Pleasure to introduce Jesse Lockley. Hopefully, I pronounced your last name
Actually got it right. Thank
correctly.
you.
Jesse is working at the University of Canberra. You are currently a senior lecturer, and previously he was at Deakin, and previous to that he was at NSA, no such agency, and CIA. I don't know what CIA stands for. So he,
Completely invisible agents.
That's right.
so he worked in the combinations of crypto and also offensive software security, I believe. That's a very unique combination. So today we'll hear from him about the quantum stuff, which I assume will be mostly about crypto, but also
Yeah.
software security. Anyway, so without further ado, please let's hear from Jason.
Thank you, guys. Thanks for coming out um, on a Monday. So this is joint work with Rolando Trujillo, who was here, I guess, last week. Sad that I wasn't able to be here. I was writing the GAN. So, all right. So it's always a little bit tricky with these quantum talks because if you get people who are sort of experts on it and you don't get straight to the quantum stuff, then they get bored. But if you have people who are not experts and you don't do any of the preliminaries, then the notation is a bit difficult. So I'm going to bias it a little bit more toward people who maybe haven't done a lot of quantum before. So first I'm going to say why should we even be interested in quantum in the area of cybersecurity, and then I'll do a little bit of the notation, and then a little bit of the areas that are important for this project. So quantum computing, quantum technology is a really broad area. I'm not using every sort of piece of it for this project. So with a relatively limited amount, you can understand what we're doing, and then sort of aim to show you sort of the technical details of the device I want to build, and then sort of the flavor of the proofs of some of the interesting things we proved, because there's one or two sort of interesting quantum counterintuitive things that we've discovered. All right, so first of all, as we start most cybersecurity talks with, we should talk about the nature of reality, right? So, uh, if you ask most computer scientists, you pick one off the street, most of them are probably think we're in more of a Newtonian universe. And then as time went on, Einstein came along, and there was special relativity, but that doesn't really seem to give you much additional computational power. So you could start your computation and get in a spaceship and go as fast as possible to light, and experience time dilation, and then your computation would be done maybe, but that doesn't seem very practical, right? So as I said, if you pick a random computer scientist, most of them will think of computation. The best you can do is in this area, and there's even a name for that thought, the extended Church-Turing thesis, which was thought to be, basically says that the best you can do is a Turing machine for any efficiently computable thing. Then on the other side, on sort of the more science fiction part of the world, I've seen a couple of papers where people think, well, what if we have these closed time-like curves, so these loops in time? Some of Einstein's equations seem to allow for that, but they don't seem to actually exist. But it would be nice if they did, because it turns out if you can talk to yourself in the past, you can compute basically anything you want. But it unfortunately doesn't seem to be the case, and then you have the Star Trek sort of era where you can basically do whatever you can imagine, and it doesn't seem like that's actually the world we live in, which is a bit of a shame, because we could all work at Starfleet instead of where we actually do. All right, so sort of the funny thing to me is that we live in this world that's neither of those. So in the actual world, we can do more than the strong Church-Turing thesis suggests, but we're a long way away from Star Trek. So we have these quantum capabilities, and they're actually quite powerful. So people have been doing a fair amount with them for math. So people figure out how to solve linear equations with them in log-in time, which is actually amazing. People have used it to attack crypto systems. So you've probably all heard about Shor's algorithm. Basically, any crypto system based on the hidden abelian subgroup problem can be attacked by quantum. There's the quantum crypto systems, where you're trying to use quantum information technology to exchange keys in such a way that you'll know for sure if somebody is eavesdropping. But there hasn't been a tremendous amount of research in applying quantum, especially early stage quantum computers, to cybersecurity. So that's what this project that I and Rolando and Arash are working on is: how can we use these quantum effects to good measure in cybersecurity. So the problem we've initially picked is we would like to secure these remote devices. So you might have a drone or a satellite or a remote power plant, and you want to know that the memory is in a particular state. Otherwise, it's not really safe to use it if somebody's attacking it. And there's a couple of approaches that people have tried in the classical regime. So there's the trusted hardware approach. Basically, you implement some sort of physically unclonable function, which is all very nice, but then you're introducing supply chain dependencies to your problem. And in actual practice, dealing with supply chain security is no easy matter. And then aside from that, your security guarantees are based on engineering. And as someone with more of coming from a math background, I prefer my guarantees to be based on computer science, mathematical approaches. So that's the software-based approach, which I'll talk a little bit more here in a minute. But before we do that, let's dive a little bit into the notation for quantum mechanics, quantum computing. This all comes from the physicists, and they picked probably the most confusing notation you could have imagined. I don't know why they did it, but anyway. So here's the basis of quantum computing: is you have a qubit. So we all know about bits. Bits can be either 1 or 0. In quantum computing, they're in a superposition. So like Schrodinger's cat, they're alive or dead. They're 1 or 0. The probabilities, coefficients are complex numbers. So you're going to have complex probabilities of measuring a 0 or a 1. And the constraint is that the sum of the squares of the coefficients have to sum to 1. So in this case, the probability of measuring state 0 is alpha squared, and probability of measuring state 1 is beta squared. And alpha and beta are just some numbers on the complex plane. All right, so there's many restrictions on quantum mechanics. So quantum mechanics frequently seems like it should put us in the Star Trek area, but it doesn't, because it has all these restrictions that are enforced through mechanisms we don't fully understand. So one of the restrictions is these coefficients. You can't extract them. So the only way, if I give you a qubit, the only thing you can do is you can measure and you get a 0 or 1. So you might think, well, that's no problem. I'll just make tons and tons of copies of this qubit, and I'll measure, and I'll converge to whatever alpha and beta are. Unfortunately, the no cloning theorem states that I can't actually clone an arbitrary quantum state. So these are the two, I would say, most important quantum restrictions for cybersecurity. Is once you've got a quantum state, you can't get information out of it, and you can't clone that state. So if I give it to you, you can't make tons of copies and give it to someone else. All right, so that's one qubit. If I have 2 qubits, then I have 4 possible things I could measure, right? So I could measure 2 zeros, and I have a probability alpha of doing that. I could measure 0 or 1, 1 or 0, and then these are my coefficients. And again, the square of these has to sum to 1. All right, so now we have one of the weirdest things in quantum mechanics is we have entanglement. So here's a 2-qubit system. What this is saying is if I measure a 0, 100% of the time when I measure the second qubit, that's also going to be a 0. So I can give Alwyn my qubit, and I go to Andromeda. Once Alwyn measures, if he measures a 0, I'm always going to measure a 0 instantly. So Einstein, we've all seen the spam. Doctors hate this one weird trick. Einstein really didn't like that because it's non-local communication, which is a big no-no in relativity. So he thought that there must be some way that the particles decided before they left which way they were going to measure. So sort of a local variable theory. Unfortunately, you can do various experiments, which we don't have time to get into now, called Bell tests, that show that actually there's no local theory that preserves realism where the particles decide at the start. All right, so these particles are communicating somehow, but there's another theorem, the no communication theorem, that states that we can't use that to communicate faster than light. So that would be really handy if we could have our devices communicate in a faster than light, non-causal way, but that's not how it works. You can use this effect, but you can't use it to communicate. All right, so how can we use this effect? So one way is teleportation. So teleportation means, again, I'm sharing a qubit with one of you, an entangled qubit, and I can use that entangled qubit as a resource to teleport instantly from anywhere my qubit, an arbitrary qubit to you. So there's a catch here. Remember we talked about the no communication there. So my qubits are in this state. So this is the entangled qubit I shared with you, and this is the qubit I wanted to send you. And then after I teleport it, I end up in one of these 4 states. So let me just try and be a little bit more clear on what I mean by that. So if this is the qubit I wanted to send, when I teleport it to you, which again instantly happens, unjammable, untouchable way, it's going to end up in one of these 4 states. And if you don't know which one it is, in expectation, the information you're getting out of this is 0, because they're all sort of orthogonal to each other. So to actually get any information, I need to know which one of these 4 states my qubit ended up on, and then I can rotate it to where I wanted it to be. And to do that, I need to send classical bits. So there's 4 possible states it could have ended up in, so I need to send 2 classical bits to actually transport this qubit. So I have this really cool effect where I can instantly, faster than light, teleport to you a qubit that can have important information related to my security protocol, but you can't get anything out of it until you get these 2 bits that tell you which of the 4 states it's in. All right, so there's one other interesting quantum effect that we're going to use, and that is control transformation. So we've all seen this logic case before, right? So this is a control not. So if the control is 0, target is 0, nothing happens. The control is 0, the target is 1. Again, nothing happens. It only flips if the control is 1. And this is a circuit that's not very interesting in the classical case, but in the quantum case, it's very interesting because the control can be in superposition. So if I have a control qubit, nobody knows what's in it, right? Because remember, you can't get the information, you can't get the coefficients out of the control qubit. So I can apply this transformation, and the output is going to be something that nobody other than the person who prepared the control qubit is going to know what it's in. So this is actually the basis of many interesting quantum algorithms, because the interaction between the target and control actually becomes quite complex. We're not going to use some of the more complex effects. That's just the effect we're using here is that I'm controlling the circuit with an input that is inherently secret in some way. So once I've created it, nobody can get that information out and know what the output of my circuit is. All right, so those are the quantum effects that I planning on using. And there's been 2 papers proposed for memory attestation using quantum effects. One of them is a software-based method. That's the paper that Rolando and I worked on. We've got a series of papers on this. And the idea is you have only general purpose hardware, be that quantum hardware or whatever. There's another paper that came out around the same time where you have special purpose hardware, and then you have to have the supply chain and all that. So I'm going to mention the basics of both ideas because sort of the contrast between them explains a lot of the challenges of actually getting this idea to work. All right, so here is the sort of the overall system that Rolando and I have. We've got a verifier and a prover, and the verifier wants to know the memory state of the prover, so he just tells the prover, attest your memory. The prover is going to do some computation that takes up all its memory. So applying Horner's rule, for example, is known to require a minimum certain amount of memory. So you run that, fills up all the memory, you hash the output of that. You're going to encode the output of that in some qubits, and then you're going to teleport the qubits. And the interesting thing about this proposal is it doesn't require you to have a secure channel here. So we analyze in great detail what happens if there's an attacker here messing with the classical bits. Of course, the attacker can't interact with the quantum teleportation in any way. The other threat model we sort of consider is what if there's an attacker over here and the prover is talking to the attacker, man on the side, and getting help. And actually, we resist that attack too. So we resist these 2 attacks, one where there's a prover, a man on the side, and one where there's a man on the middle. All right, how about our competitors? So they say that they've got a secure quantum channel here, secure quantum channel here. I don't know how you get that, but suppose that you do. Send a quantum challenge, quantum state over. You put that in your PUF, your physically unclonable unit, and their PUF basically just takes a quantum state and gives you a random quantum state that's known to the verifier. So they then use that to sample the memory, then they encode that, set the sampled memory in another state, and then they say they've got this secure channel, and then they send it back, and then they compare the two. So that sounds like a good system. And there's actually a lot of problems with it, which I'm going to talk about because then it makes it easier to understand why we designed our system the way we did. All right, so the first problem with it is it requires a secure channel. That's sort of obvious that that's undesirable to assume that you're talking securely. The other thing is that after you put your quantum state in the PUF, then you're going to have to somehow get those coefficients out if you want to read any memory with it, any classical memory with it. So you, as I said before, you can't actually do that. So the only way you could do that is if you sent multiple copies from the verifier, send it to the prover, and you just keep measuring, and then that approximates the coefficients. So if you need accuracy epsilon, you need to do epsilon squared measurements. So one of the things Rolando and I did on our second paper was, well, how much accuracy would you actually require to use the system? And it's quite high. So, but even if you only need 10 to the minus 1 accuracy, then you're going to need 10 to the 2 samples, right? So you've already got quadratic communication requirements between the prover and the verifier, which is undesirable. All right, the other major problem with this is after you've done that and you sampled your memory and you encode it in the quantum state, you're going to send it over your secure quantum channel. Once it gets back to the verifier is going to check that these two quantum states are equal. And you can't actually, again, directly compare two quantum states because you can't read the coefficients. So there's a circuit that lets you test if two arbitrary states are equal. And if they're parallel, then you always get a 1, or you always get a 0. You always get state 0 with probability 1. But if they're orthogonal, that's the best case. The memory is completely different. You only have a 50% chance to measure that they're different. So that's in the best case. You're still gonna have to run this algorithm several times to detect that the attack is happening. But what happens if the attacker is smart and decides to keep his modifications to the memory below some epsilon? Well, then you're going to need, again, quadratic communication between the prover and the verifier. So one interesting thing you can show here that is counterintuitive. So if this were a classical system, you could try and get around that by just increasing the number of bits you sample and send that over to the verifier. But in the quantum method, actually increasing the length of the vector doesn't really help you if the attacker is limiting his changes. So just to give you the flavor of the proof, and then you can check the paper if you're interested. So we have these two vectors, and we've got the memory that we're trying to encode here. So again, all the coefficients, the squares have to sum to 1. So if I have m elements in the memory that are 1, is what my vector will look like. And then in the vector that's in the memory that's corrupt, I'm going to have roughly m elements, but some of them will be different from the correct memory, right? So if you say S is the number of bits where the memory matches, you can show that S is about equal to the number of bits, positive bits, times the chance to flip a bit, and then the coefficients, and then the m's cancel out, and you're basically just left with 1 minus epsilon squared. So this is really counterintuitive that your chance of detecting that the vectors are different doesn't increase as you sample more bits. So the only way you can increase the efficiency of this algorithm that they're proposing is just run it more times. So I don't think that was appreciated when they made that. All right, so let's get on to our proposal. So what is our idea? I guess I should mention one other thing about their their method. So one good thing that this PUF provides, assuming that it hasn't been compromised during the supply chain, is it provides authentication. So assuming only this guy has this PUF and only this guy's seen this PUF, then when you get a vector out of that, you know that this guy, this is the guy you were talking to. So it provides authentication. So we don't have a PUF. We don't want to rely on special hardware. We don't want to rely on supply chain. So we have to provide authentication some other way, right? So authentication always requires that there's a shared secret. What is the shared secret in our case? When you create your device, I give half of some entangled qubits to the device, and I give half of some entangled qubits to the verifier. And our device is constructed so it can't transmit quantum information. So it can't send qubits, it can't send photons, whatever. So when I'm interacting over that teleportation channel, that I know it must be with the device because they're the only ones who could possibly have these qubits. All right. So this allows us to defend against sort of two attacks, which I mentioned before: man in the middle, and then collusion attacks between the attacker and the device. So the one of the questions here is, what are we teleporting over, right? So we just mentioned the problem you have with comparing two quantum states. So what should we teleport over? When I first started thinking about this project, I thought, oh, we'll just teleport bits. Unfortunately, that doesn't work. Why doesn't that work? Because when I teleport, let's say I wanted to teleport a 1. So this will be my 1, this will be a 0. I teleport a 1. My teleported qubit is in one of these 4 states, and I have to tell the verifier which state it's in. And if the attacker is between me and is changing my classical bits, the attacker will just say, oh, instead of a 1, he meant to send a 0. So the attacker has complete control of the communication in that case. So you can't send classical bits. The other thought was, you just do what they did in their paper, put in encode a qubit and just send a bunch of copies over and just keep measuring. Unfortunately, for a technical reason, which is that this forms a basis. Again, if you control the bit, the classical bit, you can make the verifier think you're sending anything that the attacker wants. So that doesn't work. So what actually works? And can we improve on the quadratic communication costs that we have in the other case? So what happens is we encode our memory, we hash our memory to a series of angles, and we teleport that that state to the verifier, and the verifier rotates that state. So let's say H is the correct memory. If the verifier knows what that should be, so he's going to rotate, and if the memory hasn't been modified, then with 100% probability you're going to measure a 1. If the memory has been modified, now I'm no longer completely parallel with the 1, so there's a chance then that I'm going to measure a 0. So how does that compare to the swap test? Well, this is the way you write a quantum state. You've got some angle, a probability to measure 0, so probability to detect that attack has happened is sine blah blah blah. And this is the same thing as having a dot product with 0, the 0 vector. And again, compare with the swap test, there's no 1/2 here, right? So if the vector is completely orthogonal to the correct memory, you're going to detect it with certainty, whereas in the other case, in their proposal, you only have a 50% chance to detect it. So just to make that a little bit more clear, here's our method. Again, the more different the memory is, the more chance you have to detect, whereas with the swap test, your best chance to detect for 1 iteration is 50%. So still quadratic communication required, but we're a constant factor better. This is actually the best that you can do, given quantum mechanics. At least that was our claim. All right. So what if you have this person between you and the verifier who's changing the bits? What can he do? So again, let's say this is my memory that I've teleported over. After the teleportation, it could be in any of these 4 places, any of these 4 states. So if I'm the attacker and I'm in this state, I don't want to switch to this state, right? Because this state is closer to 0, and 0 indicates that the memory is corrupt, and then the algorithm will stop. So I only want to change if I'm in this state, then I want to flip the vector to be closer to this state. All right, so basically, if theta is less than pi over 2, if the memory is less than pi over 2, there's no point for the attacker to change classical bits. So on average, how many bits, on average, how many thetas do we have like that? So we want to consider, maybe I'll skip right to the visual and make it a bit easier. So this is the whole range from 0 to 1. We want to find out what the chances are that two random points have a theta bigger than pi over 2. So that only happens in these areas. So this contribution to the average stays the same. These contributions are changed from being greater than pi over 2 to less than pi over 2. So again, we have this integral, and we want to remove the contribution from those two corners and replace it with the contribution where that angle is flipped to be small. All right, so not to belabor the math too much, if you want to see the details, it's all there. But this is the contribution to the average from those corners where the angle is bigger. This would be the contribution if the attacker flipped it. This is the total region, so we remove the contribution from that region, and we add in the contribution where the attacker took some action. And you can show that that's about 0.2. So this is from range 0 to 1, so we go back to the range 0 to pi, which is the angles we're working on. And then you can show basically you have a 10% chance to detect the attack from one iteration. So every time you do another iteration, you increase your chance of detecting. All right, so that was the man in the middle. So we also try and do these man on the side. So these distance bounding attacks, I think Rolando spoke probably at length last Monday, because that's what he told me he was going to talk about. And with these distance bounding attacks, you have your prover and you have your verifier. And you say, well, if it takes more time than a certain amount, then maybe he's getting help. Right, so if in the classical case, the prover sends something to the attacker, and the attacker talks to the verifier, and if that time is less than or close to the amount of time it would take the prover to talk to the verifier directly, then you can't detect the attack. So anytime you can make it take longer for the attacker to get the answer back to the verifier, you can protect more against these distance bounding attacks because it takes longer, so then you have a chance to detect that. So in the classical case, because all the quantum communication has to go over that channel, what has to happen is the prover talks to the attacker talks to the prover, and then you use the quantum channel. So if you add up the distances, you can see that the quantum time is larger, and therefore, if the attacker is helping you, you have a higher chance to detect that attack. All right. So I guess the final thing I wanted to say is the POF idea is something that we actually would like to sort of adapt in some way without having these supply chain problems. So how are we going to do that? One of the benefits of the POF, aside from providing authentication, which we don't need, we're already authenticating, is that you can quickly index into random areas of memory. Whereas on our method, you just do this one big computation, which takes longer, which gives the attacker more time. So instead, what we'd like to do is use that controlled transformation we were talking about earlier. Send over a qubit, or teleport it over, it really doesn't matter. And I put that qubit into my controlled transformation, and I can then get a particular bit out of that. I get a series of bits, and I can randomly index into memory. So that method is called superdense coding. You can get 2 bits of classical memory by sending one pair of an entangled qubit. And the other good thing is, even if there's an attacker here, he gets the entangled qubit, it doesn't tell him any information about which 2 bits you're actually getting. Again, because you put that qubit into the control system, and you can't get the coefficients of the qubit out, and you can't duplicate the qubit. So I don't want to say that POF idea is completely wrong, but you can get that without having the supply chain issues simply by teleporting at runtime sort of your PUF over. All right, so in a nutshell, that was our proposal. I guess the other thing to mention here is what would happen if we wanted to build this device in practice. So as I said before, the idea of our device is you have these entangled qubits that are distributed at runtime, or not at runtime, when you build the device. The problem with that is quantum memory doesn't last very long. So in classical memory, I give you a key or whatever, you go off and sit with it for 100 years, probably still be able to read it. Quantum memory lasts microseconds, or even shorter if you're using photons, right? Photons decohere very, very quickly. So I can't give you an entangled pair of photons and then say, come back to me in a month. They'll be gone in a picosecond. So instead, what you'd have to do is exchange entangled qubits at runtime, and then you're in sort of this regime, like probably you've heard of the BB84 or these other quantum key exchange algorithms. You give the qubits at runtime, and the drawback is that then to authenticate, you have to have a shared secret. In that case, the shared secret is going to be classical, so I'm going to have some classical key material on my device, use that to authenticate the exchange qubits, and then I can do my protocol. You could also think of an example where you wouldn't need really to authenticate. So let's say you've got a satellite. The satellite passes over your base station. I have line of sight to the satellite. I just pass my qubits over to that. After the satellite goes out of line of sight at some point, then I ask it to run the protocol. Similarly, maybe for a drone. The other sort of major issue that we've got here is that quantum devices, even the near-term quantum devices, well, I said even, I meant especially the near-term quantum devices are very noisy. So we did our analysis under sort of the assumption that you always get the correct result out of the system, but if it's a noisy system, there'll be some error. So really one of the follow-up papers we need to do is how would you modify your system in the presence of noise? So what is the possibility right now of building the system? It's actually the initial system is actually pretty high. So the first device we proposed, the one that doesn't use the PUF, doesn't use the control circuit, just requires gates that can work with one qubit at a time. That already exists. So Rush and I have been running around trying to find some people to give us some money to let us do that. So far, haven't succeeded there, but definitely something you could build today if you have an optics lab or you have a MRI lab or whatever. If you wanted to do the case where you have the PUF and you teleport the control qubit over at runtime, that requires at least two qubits at one go. Gates that can work with 2 qubits at one go. So that's still within the range of the possible, but then you have to deal with more noise and things like that. So I think my understanding of the state of the art is that it's still possible with 2 qubit systems, 2 qubit gates, but that's more difficult. All right, so that was my talk. I glossed over a little bit some of the math because maybe it's not of general interest, but happy to do a deeper dive or whatever. But this is the general flavor of what we did and the general flavor of the devices we'd like to build and where we're going. So thanks for indulging me.